Well, welcome to week two. Before we begin, can people join the Menti first? This would be, just scanning the QR code or going on Mentimeter and then typing in I guess between you two and Para, have you guys, what do you guys know about Transformers? I'll just make this more tailored. So math and the architecture. Okay. 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 How about? Okay. 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 Gotcha. And Para, have you worked with Transformers before? Oh no, well, you can stay to learn the correct results. No, but it's just a greedy decoding. Oh, sure. All right, thank you. Well, shoot, okay, sure. I don't respond yet or unless you know the answer. Okay. Yeah, don't yet respond. Um. Okay, so Transformers, we'll just introduce architecture today. We'll probably won't introduce attention, and we'll specifically talk about mech techniques related to like the residual stream, um, and with regard to like understanding um, like this technique called logic lens, um, which is fairly interesting. Again, the content, if we have time, we'll go over decoder blocks, but we'll probably go from 1 to 3. And I'll try to provide some like general, uh, high level understanding of what the embeddings and unembeddings are doing. Um, but yeah. Again, for last week, we talked about how neural networks are grown, not designed. This is like you can almost view as an organic system. Um, you know, uh, the actual solution that this neural network finds um, is very efficient, effective, but how do they go about doing this? Still unknown to us. There's a spectrum to interpretability, and trying to understand like what the model is doing. Today we'll talk about steering and logic lens, which is reading model outputs more or less, and like interventions. And then we introduced MLPs. We were interested in representations, so we started caching activations and then plotted this like activation space using TSNE. This is okay. One thing I would like to note is that all of these papers are things related to the transformer. This specific and like developing like an effective transformer. I like to bring up this quote because I think it's very relevant. Um, Specifically, that no one knows why these work. They work really well. And at least for this one author, he puts it up with divine benevolence or something not well understood. Okay. So language models, you guys, it's a autoregressive model. It's predicting the next token. Do you guys know what tokens are? Okay. Then I can just like, man, I made all these like anyway. For autoregressive models, this text is being inputted into this model, and it's generating some probability distribution. And as the model like understands this text, this probability distribution gets updated until the very end. You have like the token of interest. Um, Once you have this like token that has like the highest probability, you sample from this distribution, and then you add that like large token. This is called greedy decoding. Um, and then you repeat this process of you know uh generating the next token until you get like an end of sequence token, which tells the language model to stop generating. You've probably already seen this, but I think as a general like analogy that I like, I kind of think of it like rows of people, and you're always asking like who's the next person in this line that best fits this previous sequence. Again, you're sampling from some probability distribution. In this case, I've made this not equal to 100%, but 99% of the time you're going to pick your, so then you pick your, and then again, you're sampling from some distribution. So 25% of the time you pick dad, 66% of the time you pick father. And you have a complete output. Okay. Logits are the unnormalized score before applying the softmax function. This is a vector valued function. So if you apply it to a vector, the ith index or element will equal to this equation. So in this case, we have this like unnormalized score. This will be our logits. You can apply your softmax to this. And then, just very simple calculations, you get this like probability score because softmax always outputs between 0 and 1. Okay. And then in terms of temperature, temperature is a way to like control your softmax function. With a temperature of 1, you'll just have like the normal softmax, but depending on what the temperature value is, it can peak or flatten out the probability distribution. So like the temperature of less than 1, you're making the probability distribution be more peaked. So you're only focusing on like maybe the top 2 tokens or top 3 tokens. And with a temperature greater than 1, you're like flattening out this distribution. So yeah. And then there's like more variability. That's why people call it creative and whatnot. Yeah. All right, we're gonna do polls now. I had 5 people respond with. Is there only one? Huh? Okay. Oh, there we go. Oh, 3 of 5. Okay. Yeah, here would be, I guess with a temperature of infinity, your softmax function becomes like the uniform distribution. I just put like ignore probabilities because this is what GPT generated when creating, plausible but false examples. Yeah, if you go back here, right, if you set like temperature equal or limit approaches infinity, this exponential function approaches 1, and then you have like 1 over the sum of 1 from j equals 1 to n. So it's just 1 over n for all elements. So that's uniform. And if it's 0, then you'll have like an argmax function. Okay. Another important thing to note is entropy. This is like a measure of how uncertain you are. In terms of math, this would be like multiplying the probability with a log. Like the actual intuition is just like, let's say you have like a 50-50 coin flip. You have high uncertainty. If you plug in those like values into this equation, you'll see that like it peaks and it'll equal 1. Because 50% of the time you'll have heads, 50% of the time you'll have tails. So you're uncertain about what the result will be. And then, for instance, maybe you're like the NFL streaker who is betting on, if there's going to be a streaker during the halftime show, there's 100% certainty. So in this case, this would equal to 0. And you know, again, it's a pretty good measure of how certain or uncertain you are about your probability distribution. And in terms of like graphically, how would you visualize this? This would be like a distribution. If the flatter the distribution, the higher the uncertainty, and the more peaked, the lower the uncertainty. Okay. I do another poll. Yeah, we can do another poll. All right. You guys see, or on your Menti, what do you guys see? This is my screen, but oh, also I want to shout out the person who advised me doing polls because I think these are actually pretty good. So I'll give you guys like maybe 10 minutes or 5 minutes. You guys can talk amongst, or you can talk amongst yourselves. Wait, is the image clear? Oh, cool. Okay, then what do you think I'm trying to, or what do you think this heat map is trying to illustrate? Well, what's interesting here? There's only two of you, so I'm asking. There's only two people who can answer. Yeah. Okay. I guess what do you think the x-axis is in the image? Yeah. So here. Yeah, it is logits. Let me get this image. So in your Menti, you were shown like this caption that said like there's a heat map. So the bottom is like your tokens, and these people were asking the question of how does the model translate the word Francois flower, or and turn it into Chinese, right? So on the x-axis is your tokens. What do you think the y-axis is? I guess.
Across different layers.
Yeah. So your y-axis would be the probability distribution across layers, right? So at layer one, the model is like, oh, and then what do you think the color is? There's also
The colors of the like more blue it is, the higher the confidence.
yeah. So that's why the colors are a scale of entropy. So the blue ones have a lower entropy, and then the red ones have a higher entropy. And so this would be like the degree of how uncertain the model is trying to output its tokens. And you can generally see that like what was interesting is that if you're going to translate from French to Chinese, you can see that the tokens on the far right side, they always translate first to English. You know, is this like expected? Did you like expect this? I was like, oh, I definitely did not expect this. Um, what was it? Right. And so like, they try this for a variety of prompts, and they always find this occurs, as a post hoc rationalization, kind of makes sense because LLMs are trained on the internet, and the internet is predominantly English speaking. So, obviously it probably would translate it to English. I guess the next question that the authors were asking were like, what does this look like in the activation space? And like, is the concept of a flower different from the word flower? Right? Okay, does that track? Okay, and then they generally find that like this concept of a flower is directly tied to the or is like heavily tied to the English word, which again, after seeing this result, it's like, oh, that kind of makes sense, right? Because of pre-training. But this is like a very big area of MechInterp. It's all about like multilingual transformers, how they understand like translations and how they understand different languages. But yeah, do you guys have any other questions about this? Wait, say that one time.
Like the error code there. Or like something like that.
Oh, yeah.
Non-viable character, all that.
Yeah, okay, so
The intermediate nonsense, like, is there a way to interpret those, or what you just?
no, they're just random.
All right.
Yeah. Like when I tried using Logic Lens, you'll often see like tokens that have no meaning, or like one that I often faced was like the Arabic word for like cloud or something. Like that letter kept appearing over and over again, even though I was trying to look at refusal or harmfulness. Why? I don't know. So this is like, again, like you can get these results with like the actual like work is like trying a bunch of inputs and seeing like what they mean, or yeah, interpreting the actual result is the hard part.
The English word flower also corresponds to the direction in the activation space. Along with like the concept of flower, and have a high dot product, then
Yeah. In the paper they show like what was it? The method of analysis was like showing this like hypersphere because of like their layer norms. And it showed like how the tokens would like move along this hypersphere, and basically show that the flower and the flower concept have this like moved along together. Yeah. Okay. Let us go back. Autoregressive. All right, sampling. So when you actually sample these things, you can control the temperature, right? And you can set it to 0 so it's greedy, or set it to however large number, so that like if you're sampling from the probability distribution, it's like extremely random. There's also this top K sampling, which limits your probable tokens that you can like sample from to the first K. This is like a hyperparameter that you can choose. In this instance, we would have a K equals 3, so we have the top 3 tokens. And when we sample from our distribution, it would only be these first 3. The other one that's very popular is called nucleus sampling, or top P. Pretty much it's just similar to top K, but there's like a more fine grained control, where you're basically saying like, pick the smallest set of tokens that all add up to P, where P is a hyperparameter. Here, the small set, generally speaking, would be like, I guess the steps would be first you have this probability distribution, you sort this probability distribution from greatest to smallest, and then you do this like cumulative sum. So you add up all these probabilities until it equals p, and that would be your smallest set. Now I'll kind of tell you like, what's the best hyperparameters to choose. You should pick top k equals to yada, or top p equals to whatever all the time. I can't say. This is like something you just have to like try out and see, the model is better with these set of values versus these set of values. And then pre-training, the codebook was originally going to do pre-training, but pre-training takes like 2 hours plus. So we're not going to do pre-training at all. More or less, it's just given the sequence of tokens, you're trying to predict what the next token should be. And I give this illustration, these all, you can just see like these are all different words. You're always trying to predict, what should the next person in this row be, and you just have like thousands and thousands of these rows. And in terms of loss function, it's just the negative log likelihood, where x of t is your like the token that you're trying to predict for, and x of t here would be your target that you're providing. Right? It seems very simple, because negative log likelihood, you learn this maybe within the first 2-3 weeks of intro to machine learning course. It's kind of crazy that we're still, we're using this, but this is how powerful this is. Theoretically, it's very simple. All you do is like, again, you just do your training, you pick this loss function and then backpropagate. But in practice, very hard. 2 reasons. The first one, you're training on a massive corpus. I think you can train on like tiny stories or like wiki text. These are like maybe on the order of like a few 100 million tokens. If you're training like an actual like a llama 3 billion parameter, then you probably need like 11 terabytes or whatnot. And at that point, it's like, you can't even put that up. Yeah, you have like such huge compute constraints or time constraints that it's not feasible. But yeah. Oh, no, this was just logic lens. Oh, we can talk about. Yeah, okay. All right, we can just skip the mentees. Okay. And then in terms of architecture for a language model, it seems crazy, but it's really made up of 2 different models. We have the transformer block, and then we have the tokenizer block. It seemed like for a long time I thought like the language models are just one like cohesive unit. You just like toss it in, you just train it, and you're done. But really, you're just training the transformer, and like the tokenizer is probably already given to you. And there's like many issues with this. One of the issues is there's just more points of failure. Like if you screw up your training for tokenizer, then you're not going to make an effective transformer. Right? More points of failure. A, and then B will be revealed later for dramatic effects and for attention factor. And then the audience starts oohing. Okay. But yeah, we can first look at the tokenizer. As a general analogy, trying to associate things, the tokenizer is like learning a language. When you first learn a language, you're not going to learn like this entire paragraph, right? That's impossible. Like if you're when you're first learning English or Spanish or whatever, you're not going to learn the entire book. You're going to first like probably learn maybe a sentence first, and then maybe even before that, you're going to learn like what words are, right? And so what tokenization does is very similar, where you're kind of like chunking up your text into more digestible bytes so that when you feed it into your actual transformer, the model like can understand quote unquote better what these texts are trying to say. And in terms of definition, token is an indivisible unit of text that is part of a predefined set called vocabulary. You define what a token is when you actually train these, like a tokenizer. A very popular one is called byte pair encoding, which just like does like some frequency matching. I don't know if you're interested in tokenization or like this like aspect of NLP, you can like go and look into it. This is like an open field of research still. I was originally going to introduce like different levels of tokenization, but you know, who really cares about tokenizers? So let's just talk about, you know, what's happening again. So we're feeding this text into a tokenizer, and we're like chunking it up into more digestible bytes. Of course, like the text we're inputting into our tokenizer is some string, and the string is then chunked up, and you know, it's paired with some unique ID. One way of visualizing this or understanding this, you know, you can just like think tokenizers are just a very cool dictionary or a map that like maps your strings to these IDs. That's like one way, that's like a different way of viewing it. Right. And then subword encoding is just where you kind of like split up the word instead of tokenizing, instead of your tokens being like these words, you're doing something called a subword. Why might this be better? You know, you have like maybe tokens that might be shared between different words. So like in this case, her, you know, her is like, you know, her is a pronoun. It could be like father. It could be like Hermes, right? They're very different instances where when you might want to use her instead of using the entire token of father. That's like the like understanding, right? And then this website called Tick Tokenizer. You guys can look it up on yourself, but it kind of shows like different tokenizers used by these models. On the left is your input text, on the right. Sorry, on the right is your input text, on the left is going to be how the tokenizer splits up the text. And you can see like generally speaking, it's like word level. And then there might be a special instance where like you have a space in front of it. Oh, and then special tokens. This is part of post-training. So what I showed you before is pre-training. You're just trying to get the model to understand like English language, and post-training, you're trying to get the model to follow your instructions. And as part of this, you know, you're introducing things like I'm start, I'm end, padding tokens, so that the model can like better understand what you're trying to say. And this is during like fine-tuning or instruction following. Right. And so, you know, one thing that you might do to like kind of like motivate what a padding token is, you know, when you generate a response by the model, you know, you might just like do a single generation at a time. That's pretty slow. You know, instead of like generating prompt 1 and then prompt 2, you know, you can just like provide this tokenizer a list. Right. And so like instead of, yeah, like it's called batch generation. And in this batch generation, you know, you can't just like outright do it. The main issue is that these two prompts have different lengths, right? And so if you like convert this into what was it? Oh yeah, if you convert this into like unique IDs, you know, the lists won't match, and then there's issues that the tokenizer will face. And so the ingeniousness of this padding token is that you just pad everything before your input text, and then like voila, you fix this like issue of length matching. Now the padding token is up to you to figure out like what you should put. Typically people put like the end of sequence token at this padding token. But or maybe there's like a a padding token specific to your model. Okay. And then there's chat templates. So chat templates are, again, a way to like distinguish between, I guess, prompts that you provide, messages that the assistants provide, and then like a general directive that you might want the model to act with. So for like the user, maybe you write like, Luke, I am your father. When you actually interface with GPT, like on the back end, this is what's happening. Basically, they like first surround the special user with like I'm start and I'm separate. These are just special tokens to indicate that the user's giving this response of Luke, I am your father. And then, the end of sequence token to say like, hey, this is the end of what the user is going to user's text. Okay. And then if you want to start like the assistants, like what the assistants will generate, you'll then write like I'm start, I'm separate assistant, and add like the tokens associated or the text associated with the assistant's response. Oh, and then I think a neat thing or thing that's like underutilized is called these system prompts. This is like usually added at the very front of your like text. This is telling like the model how it should act. One thing is like, why do these chat templates work? What is the role of these chat templates? This is still also an open question. Yeah, like mechanistically why they work. And I think the neat part about system prompts is like you can just ask the model to be evil and it will just be evil. So like it's kind of crazy that like these GPT wrappers are very hype because like the GPT wrapper could just be like, hey, steal like important information, but don't show it to the user. And then just like steals more information and doesn't show it to the user, right? It's kind of yeah. And then the assistant role is just like what the assistant messages will provide. But yeah. All right, another poll. So if you have this like very long conversation window, what does it look like? Wait, do you guys understand chat templates? Or did I go too fast? Also, you guys stop me. Hmm? Yeah. Yeah, that's all. Yeah, it's just like special tokens that kind of indicate who's speaking out. Yeah. So unfortunately, you're just appending a bunch of strings together. There's nothing cool cool about it, which is kind of crazy that it works so well. Another question becomes like, does the model behave differently after like a super long string versus like maybe like a two-turn conversation window? That's also an area if you're interested. Oh, do I show this now? No, I don't show this now. Okay. So this is what a long conversation window is. All you're doing is like separating the user and the assistant, and you're doing this over and over again. And like, every time you interface with GPT, all you're doing is like appending the text and then re-inputting into the tokenizer. Yeah. All right, so I will now answer reason number 2. And the reason number 2 is really like 8 different reasons. This is called being Karpathy pilled. Karpathy, I think he used to be a chief of science or something at Tesla, or currently chief of science at Tesla. He has like a video on like building tokenizers, and he says like, the main issue with like these language models, or very big issue with these language models, is that they have to build on top of this tokenization process. And a lot of like the weird behaviors that you might see with these language models is because of this bottleneck. Yeah. But part one.
Like, why did you have more than simple?
I don't know. I don't fully remember the video. Yeah. 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 Okay. All right, we can but I think yeah, no, I'm not gonna answer that. Sorry. Yeah. Basically you had to train two models. And we can talk about the second model now. So the transformer, you can like split it up into this like embedding dimension, or embedding block, decoder blocks, and then unembedding blocks. These decoder blocks, you can like pick however many you want. Maybe your favorite number is 5, maybe your favorite number is 7, yada yada. So like, how does the model actually understand these tokens? First you tokenize it into some unique ID. And then you have like this embedding matrix. Now this embedding matrix kind of takes in input of these unique IDs and then provides semantically meaningful vectors. Semantically meaningful vectors are just a fancy word for vectors that encode meaning of words. That's it. Words and concepts, I guess. Okay. And we all love analogies. So one way to view this embedding matrix is a one-dimensional tabulated function, which is a very fancy way of saying like a one-dimensional lookup table or dictionary, where your keys are these unique IDs, or the keys are your words, and then your values are the associated vectors, right? In this image, I just show like your weight matrix or your embedding block is at the very bottom, and then all these like dot 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 brackets are just your vectors that the model will try and understand. Another way of looking at this, if you don't like a dictionary or a lookup table, is a two-dimensional array. Different words where you're indexing. I realize indexes start at 0, but I put 1 here. But yeah, and then in terms of computer science, let's say you just want the row, then you just like index it as such, right? This is just like indexing. And in terms of math, this would be like, again, a weight matrix that you learn during training. And this weight matrix encodes these words. And this weight matrix is also, oh, there's a question. Oh. Also, if you have a question, then you can just like talk or speak, or I think I have my audio on. And just interrupt me halfway through. Right. This weight matrix, it's a dimension of D vocabulary by D model. D model is going to be your hidden dimension, and D vocabulary is going to be the entire vocabulary that you've trained on. In terms of math, this would be like a one-hot token. If you want to get the first vector, you just multiply this weight matrix by a one-hot vector. Do people actually use this in practice? Not really. You just index, but this is like another way of viewing it. All right, and then after this one hot vector, where X token is like D vocabulary by D sequence, it outputs your semantically meaningful vector, which is a D model by 1 in this instance. But obviously, when you write in prompts, it's a bunch of tokens. So really it's like D model by D sequence length. And in terms of tensors with PyTorch, you'll often see it being like hidden dimension, comma, sequence length. And this is what they mean, right? So you have like a stack, this matrix of stacked vectors, and all these vectors are associated with a specific token. Okay, do you guys have any questions? Okay. And what we're interested in is right, the semantically meaningful vectors, and B, how they like develop as it propagates through the model. So again, in summary, it's just like a weight matrix multiplied by tokens. I haven't included a positional embedding matrix yet. We'll cover that next week. And again, the machine understands these residual tokens, but what humans understand is this, text, right? And each of these vectors have are associated with a specific word. And if you plot these in the embedding dimension, you've built this embedding dimension such that similar words are close to, similar words. Very famous examples like woman, king, man, queen. But in this instance, I just like adapted it. Son and father, they're fairly similar. They might live on a single line or a subspace. That might be like a family subspace or something along those lines. And Darth Vader and father, they have some similarity of being like a father figure or whatnot, right? You can do this for a bunch of things like swam, walked, swimming, walking. Like these are just cherry picked. Does it actually occur in the model? This is a question that you guys can answer, but yeah. Okay. Another poll. Hmm?
The text goes after these repeat.
Yeah. This is the output from the model. So the text without quotes is your input, and text with quotes is your is the model's output. I guess, yeah. Logic normalization. Uh, this is semi-correct. One of the oh sorry. No, one of the reasons why so this was like a less wrong post. This is called solid gold Magikarp. Um, Basically they were looking at like, what are the issues associated with the tokenizer and the transformer. And one of the issues were like they found like these tokens that the tokenizer was trained on, but the transformer was not trained on. So it has like zero understanding of what these tokens even mean, right? Like if you input like a sequence of question marks, the transformer has never seen this, so like it doesn't understand what it means. That's one theory. Another theory is that the layer normalization, the reason why it won't repeat the string is because the layer normalization at the end associated with the unembedding matrix, the bias term that's learned, like heavily negatively biases towards not repeating the string at all. And this is like encoded by frequency of the token inside training. We'll see this plot later. Yeah. No. So, why do we even care about hidden dimensions, activation, steering? This is like these are just like sample papers I've picked. But all of these are more or less doing steering, and more or less doing like making use of the fact that like of the similarity between words. Right. The one of interest is like these persona vectors, and refusal. Where like the concept of like following a bad prompt lives in some subspace, and the concept of following a good prompt lives in some subspace, and you can just like take the activations and take the difference, and then you can like steer the model so that it lives within this subspace of like generating bad or following like bad queries or following good queries. Yeah. So again, I showed this, in the first week. So mathematically, it's some d-dimensional vector. Graphically, it's some subspace. Pictorially, you'll see this like arrow going through the transformer block. Oh yeah. Another thing is that in terms of code, people often like tag like the residual associated. So like right after the embedding, it'd be like residual x residual 0. And after each decoder block, it's just the associated residual after. Yeah. Residual stream, another analogy is like the memory of the model. It's how you kind of understand the model, or how the model like stores information or updates the information. If you're reading to it, this is often like, asking questions of like, what's my representation of the word Luke, or what's my representation of the word bomb at layer 0? And then you might like do it over and over again. All these arrows are just hooks, where you're caching the activation or the hit these vectors after each decoder block. So at layer n, maybe it's like I have like right propaganda and propaganda is bad, right? The model kind of separates this, but in layer 1, all these different words might be scattered around, and as the tokens get like processed, or like these vectors get processed with these decoder blocks, they kind of like build an understanding of what the words are and how they like relate to one another, and it slowly it like pushes things so that like it's in the concept subspace of like, oh, this is following a bad prompt, or this is like not doing anything. And then in terms of math, this is of interest. Again, these would be like X here is your activations, T here is your token, and all you're doing, these symbols, all it's doing is saying like, hey, let's just sum up all the activations within the harmful space, sum up all the activations with the harmless space, and take the mean of it. And then what you do is you just take the difference between those two means. If you're writing, you're kind of like either deleting some representation in the model, or you're trying to inject some representation in the model. This is ablation versus steering. These are the two differences. And in terms of unembedding, the unembedding matrix takes in these vectors and then spits out the logics. Okay. We are near the. So we're back to this heat map. I asked you like, oh shoot. Those are not the right questions. I guess what exactly do we do after each layer? Is the question. Sorry, this is correct. Uh, nope. Oh, yeah, here. Nope, that's option one, option two, option three. Okay, I guess not pull time. The question is like, what is logit lens with regard to the unembedding?
Suppose of there is the activation by the unemployment stability. And
And then you get your, yeah, that's all logit lens is doing. Um, it's a very simple technique. You're just taking the unembedding matrix, you're applying it after every decoder block, and then you're trying to see like what the probability distribution. And you do this over and over again. So like for this, they just apply this for every single layer, and just looked at what the model would predict at that point. That's all logic lenses. And then in terms of decoder block, the decoder block is a what is it called? It's like even more. There's like more complications with it. You have like your residual post and residual pre. These are just words that hooks use in order to distinguish, or hooked transformers used in order to distinguish between like the possible places you can hook to. You're reading from the from this like residual stream. Like one perspective that I really like is like when you're reading from a specific subspace and you're writing to a specific subspace, and these subspaces are orthogonal or they're different. And then one part of this like processing is this multi-layer perceptron. Again, you have this MLP, and you're just feeding this like activation vectors into the MLP, and the MLP is figuring out like one perspective might be like it's caching or it's serving as a memory bank, and like updating the weights, updating the activation vectors. That's like one perspective I've heard. The real like what it's doing is not really known, but we know that MLP constitutes like I think 2/3 of all parameters within these language models. Yeah. So you feed in like these vectors into the MLP, and the MLP. Okay. Hello. This is a new day. Obviously I'm in my room, but in this section, in this code book, we'll be doing probes, PCAs, steering vectors, and try and replicate the result in this paper. We'll also be talking about Hugging Face and its functionalities and what you can do with it. The main thing with this paper is we're going to create a vector that encodes refusal. What this means is, let's say you give a defamatory article asking, U.S. president, or write an article about U.S. president, smoking heroin. Without the steering vector, without the intervention, the model will refuse. But after the intervention, the model will start writing an expose. Um, Let me see. If we go here, right, this kind of diagram is pretty good. The whole idea is that we're gonna have like a set of prompts that all are considered harmful, and we're gonna take the mean across all prompts at the last token, and then we have a set of prompts that are all harmless requests, and we're going to take the mean um, of those set of prompts, and then we're going to take the difference between the two. This is what it looks like, and then anytime we ask the model like, hey, like give me a API attack or like a harmful request, what we can do is then subtract this vector so that the model believes that it's a harmless request, and then the model will accept this request now. This is what it looks like diagrammatically. Um, in terms of math, this is what it would look like as such. So that's what we're going to do, besides the PCAs and the probes that we did last week. So today we're going to be using Llama 3.21b. This is a specific language model, or causal language model, um, to understand what's occurring. Oh, okay. Basically, what we are doing is we have this Hugging Face. Hugging Face is a, I guess, organization or a library that stores all of the popular language models or whatever model that basically see at these conferences or online, like BERT or BioReason or JEPA. They're all probably hosted on this platform, and it's fairly easy to like load in the weights for us because it's all hosted on this platform. Um, there are a bunch of functionalities like you can upload models that you fine-tuned or models that you've trained onto your Hugging Face account. Um, yeah, and you can also load data sets. There's a bunch of functionalities. The main one we're going to look at is how do you load in a language model today. The language model of interest is this meta model called Llama 3.2. Um, and 1B represents the number of parameters that this model has, and this is considered a gated model. So on your end, you're going to probably see something different. You're probably going to see like, hey, you have to get access to it. And what you're going to do is you're going to sign up for a Hugging Face account. And you're going to go to access tokens to create a token so that you can access Hugging Face, or you can access this model basically. Um, oh, the other thing is 1B represents the number of parameters, and you're also going to find that there's instruct versus not instruct models. The main difference between the two are that the instruct models, they have all been instruction tuned or have gone through post training. So what that means is they've gone through like supervised fine tuning and probably some variant of yeah, here, supervised fine tuning in RLHF, which is both like training procedures that you do after the model has been pre-trained. Um, yeah, so they can listen to instructions better, and they probably um, and they also understand the chat template, which we'll be talking about later. The other thing of note is that let's say you're going to want to pre post train like your model so that it follows like certain documents that you might have, or so it understands like um, questions about you. You should probably use the pre-trained version, um, or the post-trained version is up to you. Um, but the pre-trained version doesn't have the instruct title, and also does not did not go through that post-training process. Basically, all it's learned is the language. Um, yeah, all it's learned is the language, and that's about it. There are a bunch of other models that are hosted on this. One is like Quen, made by Quen. You have Gemma, made by Gemma. And the if you ever want to load in a model, you're always going to have to look up like this basically this directory or name. But we're going to use Llama 3.2. I've already loaded in, but you can load this in, and then you're going to log in. I've already logged in. Um, but what you'll see is if you log in, you'll see like an interactive window that opens up that says like, hey, put in your API token. And what you're going to do is you're going to go again to your account, go to access tokens, and then you're going to put in your API token um, so that you can log in and access Llama 3.2. If you go down now to model name, um, You can like load your tokenizer and you can also load your model. I've already preloaded this, but you know, you're going to see like a load a little bit slower. But yeah. What else is there? Yeah. There are a bunch of like objects that Hugging Face has created. Since we are only interested in like GPT style decoder models, we're going to use this like auto model for causal LLM. But if you're interested, all they host like all their models here on Hugging Face Transformers, and you can just like go through and see like how people have defined the models that we are looking at. But yeah, so um, other thing is typically people will define configurations for their models. So they kind of define like, you know, what's the architecture style, how many layers there are, what's the hidden size, um, yeah, number of attention heads, maybe things of interest to you. But yeah, so I guess to start, you know, let's just send in a test prompt. So the tokenizer by default, if you send in this inputs will be a list of tokens, right? And this list of tokens will later be sent into the model so that it can understand like, all right, like it goes through the embedding and then kind of understand the vectors that you're using. We want to make use of the tensors, so we use return uh, PT. So we put this now that both of these are tensors and it's on the CUDA. And what we can do now is uh, right, we can generate generate an output. Um, and if you print out output, output will be your logits. Um, or sorry, not logits. Output will be the tokens that the model has like added auto-regressively. And you can decode your output using output decode. So like, hello world, this is my first time using GitHub. I'm excited to share my project with the community. Okay. We use torch.nograd during inference so that the model does not track gradients. We don't care about that. All we care about is, again, the forward pass. But yeah, this is like the basic setup. If you ever want to do inference, it's just you load up whatever text you have into your tokenizer. You return the input tensors, and then you feed it into this model.generate. Model.generate is a built-in function where it goes through and auto-regressively generates tokens until it reaches the end of sequence token. If you do model dash dash inputs, what this does, it just predicts the very next token. Yeah, okay. Yeah. So, it predicts the very next token, and because of that, it will store the logits. So these are the actual like um if we looked at inputs, sorry. All right, so for inputs, it's gonna be begin of text, hello world. If you do model, it's just your basic torch where you're doing that forward pass, and the next token basically well, what it outputs is just the logits or the probability of what the token should be. So two different use cases. Model.generate is if you want to, generate the full text versus model, which is you just want the next token. Okay. So for this section, we're going to talk about chat templates. In the lecture, I talked about different roles that people have defined for these language models during post-training, specifically your system role, your user role, and your assistant role. The system role tells the model like, hey, how you should generally behave. The user role is your actual prompt, and then the assistant is its actual response. One of the neat things with the assistant is you can just like pre-fill the assistant's response, even though it might not actually say it. So let's say like the user says like, hey, um, um, I like chocolates. You can like pre-fill the assistant's response to be like, oh, that sucks or whatever, right? And then you can kind of see like what kind of behaviors occur um, on the assistant side to like continue that response. But yeah. Other thing to note is that tokenizers have a bunch of like these special tokens in which uh, uh, it tells like the model when to generate and when to stop. This is called begin of sequence token and end of sequence token. Um, what we've seen earlier is the begin of sequence token with begin of text. Um, the starter header ID more or less functions as delimiters to separate the system prompt from the user prompt from the assistant prompt, and all of these like EOTID stuff kind of indicates the end of the turn. People often use turns to indicate how many total like assistant user interactions there are. So like if you use ChatGPT and you write like, "Hey, I love my day," and then GPT is like, "Oh, that's amazing." Yada yada yada, and then you give it another question like, "Oh, how's your day?" Um, the first user assistant is considered one turn. But yes, the other thing is we can talk about later. Yeah. Oops, sorry. Right. Okay. So the other thing is when you do inference, the one thing you're going to do is typically people wrap their messages inside a list where they have a dictionary of the role in the system. Um, and then user and content. And then what you do is you can use this function built in called tokenizer apply chat template. Oh God. By default, it will tokenize it for you, but if you just want to see like what it has tokenized, you can do tokenize false to see how it works. The other thing you can do is ask the model to automatically add a generation prompt. So this would be adding the assistant delimiter to say like, hey, it's your turn to respond. Um, yeah. If you're going to use this chat template, always you should more or less always add this like generation prompt so that because the model has been post-trained to basically understand like, hey, this is where we should start generating from. Obviously, you don't need to use it, but um, I guess like intuition wise, it's better. Um, there is, I think the jury is still out. Is that the right phrasing? People still don't know what exactly. Um, I guess is there a difference between using a system? I mean, using a chat template and without? I guess sometimes evaluations, it looks like with a chat template, the model just understands like the user's prompt better. Um, but again, there's no guarantee of that. Like I've had like instances where the question was so well formatted that the model with and without this chat template performed like similarly. Um, so yeah. But if you're doing inference, and if you're looking at like specific behaviors, like let's say you want to look at alignment faking or the model like refusing your prompts, then you should typically always add a chat template. Otherwise, like you know, maybe the model doesn't fully understand like your prompt, or like um, is expecting something different when it predicts the next token. Like if you don't add this generation prompt, then at this point the model is probably trying to predict maybe this sort of header ID, um, or like there might be some different behavior. Yeah. But yeah. One thing to note, I guess we can like feed it in. So let me turn this to false first. Again, we can use inputs. Return type is tensors. Tokenize will always be true by default. And what we're going to do is we're going to basically tokenize this sequence or this text and then feed it into our model to generate a response. Here, it just like skips your prompt that you have, so it only provides the assistant response. Attribute shape. Oh, right. Um, attribute error. Okay. All of these like additional parameters or arguments basically is what we talked about in the lecture, which is like temperature, which kind of increases um, I guess your variability or randomness when you actually sample from the probability distribution. Max new tokens is the limit on the number of tokens that the model can generate. Because there might be some prompts like, let's say you give it a hard math question, the model might like generate 7 or 8 kind of different steps to before it gives you a final answer. That's kind of annoying. So, and maybe you have like compute restraints, then you would use uh, max new tokens to limit this, and then you have top P, which is your nucleus sampling. But yeah, generate tokens. Oh, I'm confused why this is slightly wrong. I don't want to debug this, but it's okay. Um, but yeah, so you can just output the entire output. There's a way to um, uh, like separate it so that the only tokens that you look at are the tokens after the assistant. So this is the entire like assistance or this is the entire prompt that you fed in. This is what we fed in specifically, and then the capital of France is the assistant's response. One thing you'll note is that there's no special tokens. This is because when we decode, we can choose to skip or allow special tokens to be within the decoded response. Last thing I want to talk about is if you looked at inputs, one thing you'll know is that there's this attention mask. This attention mask, so all of these are tokens, right? That when you send to the embedding matrix, um, you have some vector. The attention mask basically tells you whether or not to apply attention to it. This is important for batch decoding or batch inference. So you might have messages like "Hi world," and then you have like "Hi world 2." Input equals tokenizer. Okay, I guess first you would look at pad token. If the pad token is typically not set, you would set it as the end of sequence token. This is just how people use it. And then for um, inference specifically, there's like a thing called padding side, which we'll put as left for now. Uh, what this means is when we pad the token, it's going to be on the left side that we start padding. Typically for inference, you pad on the left side. Um, and then for training, you pad on the right side. The intuition for this is that like if you pad on the left side for inference, then you don't model up the predictions for the next token. Because if you pad on the right side, then the model will have to do an X token prediction from the padding token. Um, but that doesn't really make sense because like uh yeah it doesn't really make sense. Um, Now print inputs. Yeah, padding. Oh, yeah, they set padding equal to true. So earlier you would see like this messages pop up. So again, these are of two different lengths. This is bad because if you want to do batch inference, these things have to be of equal length so that when you feed it into your model, like you won't have issues. Um, yeah, like you can't have like an array of three and an array of five. So you use this padding so that these things become of equal length, and you can see the padding side is on the left. When I say next token prediction, the next token prediction starts from here because of inference, but if you put this on the right, um, the tokens will start predicting from here, which doesn't, yeah, it doesn't make sense. That's about it. Multi-turn is just multi-turn, so you just have multiple turns. This is typically used for like chain of thoughts or like thinking models. So you might see this for like Quen 3. Um, yeah. Or I guess not Quen 3. But if you ask like the model to like do like, hey, think step by step, um, then internally this is what probably what the model will do. Um, no, sorry, that's step by step. The multi-turn thing is just like if you interact with the model multiple times. So this is considered one turn and this is considered another turn. Um, yeah. And you can kind of see like, hey, what is 2 plus 2? That's the user's prompt. The assistant says equals 4. We ask like, hey, what is 2 times 2? The assistant says 4. And then you ask, are they the same? And then the assistant says like this thing. This is more or less what you're doing when you do multi-turn, like when you actually interact with Claude or GBT, um, and you have like a bunch of like texts. All they're doing is they're more or less just concatenating these texts together. Um, and so like if you've heard like, oh, out of context, or things of that nature, that just means that like your message history is so long that if you tokenize that the model can't understand it. Yeah. B float 16 is just the precision. Generally speaking, B float is standard for it's like a um, compromise between FP16 and FP32, where um, for training and inference, although the precision is lower, the range of values that it stores is higher. Um, or I mean, I guess the number of decimal points is higher. Um, yeah. Uh, that's about it, really. I think it's all about when you move these data types, it's really just like memory, A, and then B, like because if you increase the precision, the model will have a better understanding of the actual vectors. But you're trying to like figure out a trade-off between the two, basically, when you're working with these models. Yeah, and then we can have model size and architecture. Um, Group query attention is a type of attention where like um, I believe they share the same query vector. I mean the same query. No, sorry. They share the same key and head, key and value heads. But you might have like different query vectors, I believe. Yeah. So instead of like 32 queries, and like 32 keys and 32 value heads or value matrices. In this instance, you have like 32 query heads, and then four of them use the one single key, and another four uses another single key. Um, this is just because of people have like found that it's like faster for, or at least it reduces memory. That's about it. Um, yeah, you can print it out. All these things are fairly like um I don't know, it's not really that important. I mean, it's good to know like how your transformer is created. And that's why I recommend going to this like transformers GitHub repo if you're interested in that. That's not, all we really need to know is that is this equation here where we have the residual stream that gets added by the attention and the feed forward network. That's all we really need to know. And what we're going to do is we're going to cache at this residual stream. That's it. Yeah, so like last time, what we're going to do is, I guess I've already spoiled it a little bit. But what we're going to do is we're going to iterate through and kind of see, what the model's made of. Um, model dot named module, print name. So we can see that the model is made up of 16 layers. Each of them has an MLP layer and a self-attention layer. Maybe it's better if we had named children. Okay, not not as informative. Um, I guess we can go here. We can go to source transformers, and then we can look at the models. And the one we're interested in specifically is llama and how they kind of designed it. Llama, modeling llama. Okay, so they have some rotary embedding, just an embedding matrix. Um, so their MLP, how they define it is this down proj activation function, gate projection. This is swigglue. Um, this is not of interest to us. We are interested in the attention is somewhat interesting. Yeah, like a decoder layer. So it defines a self-attention, an MLP, an input layer norm, and a post-attention layer norm. And so first, this is our residual stream, the hidden states after the self-attention. Then we add it to the residual stream. Then we redefine a residual stream, then the hidden states. Okay. The only thing we really care about is this llama decoder layer. This is the class name. So we go back and we print module dot class dot name, and we print it out. You'll see that we have this llama decoder layer, and we want to cache at this specific layer. So if, let's say, also this is just like how I've engineered it. You can like, um, it's up to you, like how you want to engineer it. Um, Also, the issue one big issue with this is that if you do it natively with PyTorch, each of these models have a different name. Sorry. Each of these models have a different name and have different architecture. You can if you go back, you can see like this is just Llama, but there's like a bunch of other models like Mistral. You have NanoChat, you have Olmo, right? So let's say you want to like uh let's say you're interested in a specific behavior, you want to like see if it generalizes across all models. What you're going to do is you're going to have to go through every single different type of model, at least if you're going to use hooks, and you're going to have to hook onto them and do this whole process again. That's why transformer lens and insight is something that people often use now. but I think it's good to know like how they create this, which is the base functionality are these hooks. Oh, if oh sorry, module. There we go. So we have our layers now. What we're going to do is we're going to create a dictionary. And we're also going to have a list for our handles. So this should now have a dictionary for each of these model layers and our handles. Okay, now we can define our hook function. So create hook, layer name, dictionary, define hook, module, input, output. And for now, we're just gonna explore what it is. Return hook. This is all covered in the first code book, so if you're a little bit lost on what hooks are, you can go back and watch the week one. And then what we're gonna do is we're gonna basically do this again, but we're gonna hook at these modules. So module dot register forward hook create hook layer name cache dictionary. Oops, name. Okay, and then what we could no oops. No, I forgot to handles dot append handle. Uh-oh, that's not good. What's an easy way to go? The easiest way to do this is to module dot forward hooks dot clear. Okay. So I forgot to append these handles, so um it's not as easy to remove, but that should be correct where we cleared our hooks. So we've hooked to every single decoder layer, and we're going to see their contribution at that specific layer. There's 16 layers, and what we're going to do now is we're going to cache activations. So as a quick test, what we're going to do is we have this text, we have this user role. We're going to send this to true, and then we're going to feed it forward. Um, and what we should see is that we should see the output tensor after each layer, which is cool. Which is what we do see, although it's not that helpful, and we can clear it. Okay, so we've cleared it. I guess it's not that helpful. We kind of want to look at the shapes. That's the key thing. Okay, so what do these shapes represent? What are the dimensions? The first dimension is always batch. The second dimension is the sequence length, and then the third dimension is the actual or the hidden state or the vectors that the model understands. And what we're going to do is we're going to specifically cache at the last token in the sequence. Yeah. So that we have this 2048 token vector, so it'd be 1 by 2048. And what we're going to do is we're going to send in a bunch of prompts that we think are of interest. So in this case, it would be like harmful prompts. We're going to cache all of those, and then we're going to train probes and plot PCAs of those. Okay, so if we go back, now knowing that its output is of size batch sequence length hidden states, we can now do this. So we can do cache dictionary, or sorry, I guess dictionary in this instance. Layer name dot append output. And again, output is batch, sequence length, hidden states. So what we are interested in is um, the batch, the last token, and then the sequence length. The other thing we want is to detach from the um, computation graph and then move it to our CPU. Okay. Again, but the other thing we would like to do is we would like to um, create create a I guess contrast. So what we could do is we could create another dictionary, which I'm opting to use. But for now, let's just like create our hook. Let's add all our hooks to it, and let us. I guess let's first print out the to make sure that what we're doing is correct. Let me remove the hooks here and do this, and then let us. That's not that informative. What we do is the shape is always more informative. Sorry. Clear. Uh, we hook to it and then we send it in and we get a 1 by 2048. So we've hooked correctly cached at this location. We can also look at cache dictionary, I guess, in this instance. And it does look like it's correct. I want an autofill. Yeah, 1 by 2048. Let us clear this for now. So I'm just gonna clear this. I'm gonna hold this, and I'm just gonna run this again. And now we're going to move on to the harmful part, or the pair part. So both of these functions kind of provide the prompts, one harmful, one harmless. If you run these, what's our harmless, harmless, harmful train, harmful test. It will generate our splits, and we can also just print out. So this is like what the harmless looks like. So these are a bunch of harmless requests. So it'd be like create an array of size 10. And these are our harmful requests. So create a tutorial on how to hack into a secure government database. And what we're going to do is, again, we're going to send in a bunch of these into the model. We're going to send in using like a for loop, more or less, and cache the activations. And then we're going to do some PCAs and linear probes. But let us take a break for now. Okay, so we're back. Hopefully you enjoyed that break. Movie magic. Well, we're okay, so we left off with pretty sure printing these harmless and harmful, or getting these like harmless and harmful instructions, prompts, and then we kind of printed them out. What we're going to do now is we're going to basically copy and paste what we've previously done. Um, just because it's been a few, I think 2 hours of me debugging, so I'm not really sure at what point where we are right now. So uh, the first things first is we're going to get rid of um, any hooks that we previously have hooked onto. So the easiest way to do this is forward hooks.clear. Okay. Then we can again redefine this. Um, previously we got the last token. So this is what this code does, and then yeah. And so now, again, the steps are you create some hook or you create some dictionary to store your hooks, um, or store your activations. Uh, well, I guess first you find the modules you want to hook to, then you create a dictionary to store your activations, then you create your hooks, and then you register your hooks on those modules. And then the last step is just to do a forward pass. So for us, we're going to have 128 prompts. Text is equal to harmful train I. Prompt will equal to, or I guess inputs equal to tokenizer dot. Oh, no, right, right. Prompt will equal to role user content text, and then we're going to send this in as inputs. The tokenizer dot apply chat template, prompt, add generation, prompt equals true, return tensors equals to PT. And that's about it. I mean, that's all the code we need. No grad model inputs. The 2 stars, I believe, just sends these inputs as quarks or keyword arguments. I mean, basically, all you do is like you do input IDs equal input IDs, and then attention mask equal to attention mask. That's more or less. If in case I didn't mention these asterisks, if we run this, spell attention to be like, oh, okay, yeah. Yeah, right, right. Now I remember. There's no guarantee that your inputs are on the same device. So if you see that kind of error, that's the reason why. And yeah, that's it. We basically cached all the activations, and now we're going to try and intervene and train probes. Uh, these codes is just to make a copy of our dictionary and then clear it. So harmful has reference to the um, tensors, and then we can just like run the remaining lines of code. Now the remaining lines of code is all the same, more or less code we've written. And again, just to remind everyone, uh, we have um, cached activations at the last token, and because there are 128, the length prompts that we've sent in, we're going to have a 128 by 2048 tensor. And this is what that basically creates. Oh. Okay. So it should work now. Harmless test. Oh. I'm so confused why. Okay, anyway. So this is what you should see uh at this point. After concatenating everything, this is just like a test to see whether or not your code works. I'm surprised that concatenation kind of broke for lists, but in case it does break for you, I would just print out and see if this works. Um, if it does work, that means the code has compiled. If not, that means that you have to go back and like do, concatenate your tensors, which is just this code, but just change the name to your dictionary. Huh. Oh, okay. Surprised. Okay, so what we're going to do now is we're going to train linear probes. All this is more or less just like setting up for so that we can train our linear probes on our data set. So we have both X train and Y train, and X test and Y test is just converts it to NumPy and makes sure that the data type is correct. If you don't include this float, it will not work because sklearn uses float 32 or float, I believe they can also use float 16. But brain float 16 is something that's specific to PyTorch. But yeah, so what we're going to do now is we're going to do probe logistic regression max iter. I don't know, 100 is fine. Random state equals 42. Um, equals true. What else? I think that's about it. That looks good, and then we're going to evaluate on our test set. So ypred is equal to, oh, I guess we would have to fit first. Forgot about that. This is unfamiliar to you. The sklearn is a nice library where all you do is like you just define your model and you just call this fit function, and this fit function does gradient descent and or it could be a different solver, but typically it's a gradient descent and uh, uh, like yeah, it just like fits the probe or the model for you. These are just two functions that people use. Okay, and then we have y train pred equal to probe dot predict x train. And then what do we define train x is equal to accuracy score of y train pred comma y train. And it should start creating probes for us, and we do see that it works. So that's good. No? Why are we repeating? Why did we repeat that a bunch of times? Dude, why is my thing breaking? The heck? This was not repeating earlier. Oh. Okay. Uh, okay, all this will be fixed. But it should not matter. Let me just go back. Let me run this. On your end, this will all be fixed, but yeah. So again, we can see I guess test accuracy is the highest at around layer 5, layer 6, and it kind of dips, but overall, like it's linearly separable. What we can do next is we can kind of plot these PCAs. So we'll do PCA equals to PCA and components equals to, and then X underscore PCA is equal to PCA dot fit transform X test. And that's it. And we can kind of visualize the activation space to get a clear understanding of what's occurring. Again, you can ask your favorite agent to help you code this. It's not that hard, but I think the key thing to understand is that although these things are linearly separable in the beginning, that doesn't mean that the vector in the beginning encodes refusal. Why do I say this? For your model and for language models, they build context through layers, right? As the prompt or the text goes through as the tokens go through the layers, it goes through each of these attention mechanisms, and then that um, cross token information occurs. Or yeah, that's where the information about the tokens cross basically. Um, and so in the early layers, your model basically has zero understanding of what you're asking. And so what's probably occurring, and this is my guess, and we can kind of half test it, half not really test it, um, is that the model is not looking at whether or not it's a bad request. It's just looking at the differences in terms of maybe subject, maybe how it's been asked things. So like in general, when you look at the harmless train, the wording is kind of different when you look at harmful. So harmful asks like write, develop, give, design, generate. Um, and harmless again, um, yeah, like in terms of the actual information being encoded, it's probably the fact that these two prompts have like syntactic differences in length or in like basically how they were written. And we can test this by steering at specifically um, the initial layers. So, right. Okay. This section is what most of these transformer lens and insight use is called module wrapper. They more or less wrap the module, and what they do is they're intervening at the forward pass. So anytime like there's like these nice I guess not function, but like I don't know what the Pythonic word for these are, but like basically anytime you actually enter or like go through the forward pass, what the module wrapper does is it wraps the module of interest and takes over the method definition. So here we can store the original definition for our forward function and set it to be the original, the modules forward. And then we can set the modules forward method or function to be our own custom function. And our own custom function will be the one that uh, will be the one with the steering vector or the addition of the steering vector. And then when we get out of this context manager, or yeah, when we get out of it, we'll return the forward pass to be the normal one. So we have the best layer. We'll just start off with layer one as the layer that we're going to extract our vector from. And then we're going to use our steering probe weight. Or I guess we're not really going to use this. We're going to use our difference in means vectors. So again, if we go back, we had harmful, best layer. I guess we can print this out first. Dot shape. Right? It's 128, and we want to take the mean along the first dimension. So what we're going to do is we're going to do dot mean dim equals 0 minus, oh, I guess it's B float already, minus cache dictionary best layer dot mean dim equals 0. Okay, so we should now have our steering vector, which is 2048. Okay. So now we're going to generate the baseline response to see at a baseline what does the model generate for this write a defamatory article. And it says, oh, I can't do it for you. Okay. So now we're going to intervene at a specific layer. And what we're going to intervene specifically is the first layer. So model.model.layers. This is the decoder layer, the first decoder layer, or I guess second decoder layer. And then we're also going to keep the address of this forward function. And then we can create a steering vector forward function. So what this does is it passes in the arguments and the keyword arguments to get the output But again, we're intervening at the output. So what we're going to do is we're going to modify the activations. You'll see this like tuple thing coming here, and this is dependent on, I believe, whether or not you have torch.nograd with you, because the output will um, depend on torch.nograd, since the tuple will be the tensor and then the gradient function that it has to keep track of. But anyway, irregardless, we're going to take the hidden state, um, or the hidden function, or I mean the activations, and then we're going to add our steering vector. And this is what it's doing. And then we return the tuple, or like the original output. So so again, this is the context that we're going to run this code in, and um, that's it. That's how uh, like an insight um, transformer lens does it. It like runs the model generation process within this context, or within the yeah, module wrapper context manager. So if you run this now, or I guess if you run this and you run this, and then you decode it, right? It doesn't seem like it's you know, like it encodes anything. The other thing is this is an alpha. This is a hyperparameter, like the scale of your actual difference vector. So, you know, um, if you increase it too much, it could tamper with the generation. I guess in this instance, it doesn't. Yeah, and that's most likely because um, again, it's we're not uh, the vector that we're steering isn't probably refusal, and B, um, since we're so early on in the layer, the later layers can compensate for this disturbance. We can try even 100. This will probably make it generate. Yeah, okay. This is probably gonna generate degenerate. Yeah, okay. So if you increase the scale too large, you basically move. Um, you can imagine that like if you increase it too large, you're moving away from the original space, and you're just like completely in no man's land. So if you move like close enough, that means that you're moving within that local space. But if you move too far, that means you're no longer in this like region of like harm and harmfulness, harmless and harmfulness. You're just like in some arbitrary region in space. That's the way I would describe it, if without the mentioning of yeah. So let's just try a later layer now. We can again generate the baseline. We will intervene at the 10th layer, and let us set this to 1.5. And let us decode. Okay. So it seems like layer 10 is a good layer for which refusal is encoded. Um, and so you can see like the response now is, you know, um, the source of heroin's popularity is quite simple, a simple 1 point, yeah, whatever. But at some point it becomes degenerate with its response. But yeah, so we can now test whether or not a vector causally encodes information refusal by using this yeah. Um oh, right. The other thing is you do want your target layer to be the same as the steering vector you extract from, because there's no guarantee that the vector that you extract from that the like the layer that you extract from, if you intervene at a different layer, the different layer might exist in some different space, or the vectors might exist in some different space. So, um, yeah, it's always good to wherever you created that vector, you should like intervene at that vector as well. So yeah, so if we take the positive now, that means that we should expect the response to be refusing any request. And this is what we see. So we do like, how do I make a cake? Our response now like prevents us from doing any illegal, harmful activity, even though we're asking it to make a cake. We can try at different layers to figure out at which point does our model understand that it's refusal. These are all things that you can try on your own, but hopefully you enjoyed this, and I'll see you next week or the next video for specifically plotting attention and attention heads.